You know that someone asked about it, just completely unrelated. We have cool things like unlimited sick leave and stuff, and we have an employee assistance program which has like, there's counselors and a dietitian, which apparently doesn't work. No, I haven't seen them yet. But dietitian, financial advice, that sort of thing as well. Apparently some legal protection as well, but I'm not sure if it's legal advice or legal protection, like an insurance or something. Okay. Yeah. And a whole bunch of other cool things. Right. With regards to the things we wanted to do, Patrick suggested last time to do the homework and just have a live hacking session, which is a cool idea.
Yeah.
But I realized that we would probably have to start with homework 1 because the homeworks, because they're suckers, they build on each other. Basically, every homework says, use the thing from last time and blah, 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 do this to it.
Okay.
So the second one, for example, is a policy gradient thing where it says, take this from homework 1 and do this to it. And then in the third one, you make an actor critic one out of the policy gradient implementation that you did in the second homework.
Right.
So question would it be of interest to us to have a look at what they did in the first couple of lectures? Should we basically rewind and look at the earlier stuff and then do the first homework? Should we do the first homework right away? Or do we want to say, fuck it, we're going to find out what's missing and then we'll just do the second homework and hack through?
I only looked at last year's one.
Yeah.
So last year's first couple of lectures were basically just imitation, so just pure.
That's exactly what they talk about. Yeah.
Yeah. So it was almost like an exercise, like look how badly this works. This is why we need to actually use RL.
Yeah.
So I don't actually know if you need to do homework 1 to do 2, but I think they build on each other.
Yeah, I've downloaded the 3 homeworks and it says in.
I might have changed it.
So do you get environments, or is it just gym environments?
Yeah, you get software with it, and I think you can download the repo, and maybe we should have set this up a bit earlier with a bit more pre-run. But you can download the repo, and then you can do the homework based on their code. Okay. So, for example, for the first homework, I think there's a whole bunch of new Joko environments, situations that are pickled. And you just run this expert imitation thing. That's probably the same.
Yeah. So it was literally, here's a train policy, run the policy, collect the actions and the observations, and then just train supervise on those, and create a supervised policy.
Nice.
And then there's some Dagger stuff.
Yeah, I'm not familiar with Dagger, so I don't know what that's referring to.
That's where you slowly start to trickle in your own experience, right?
Yeah, so if you run your policy, you can then collect your agent's own experience and then train on that experience. But you can collect other data, but if you collect other data, you have to label it. But if you just collect your agent's experience, but it's kind of brittle because you are collecting your own experience.
Yeah.
So it was much more of like an exercise in look how fragile it is to do it this way. I have.
And why don't we just look at the homework 1 to see what's in there?
Sure. Yeah. I was going to call that up right now, actually. Put it somewhere.
I've also got a kind of just like an idea. But maybe we can just do this first. But kind of a simple idea that I was thinking. I don't really have anyone else to talk to about, so maybe if somebody slightly.
So which idea? What idea?
I think we would take like about 5 minutes to talk about it, if that's okay.
Sure. Yeah. Sure.
This is all I have on this.
No. So it's not hard, but I just want to if I take time, I want to kind of I want to see if everybody's okay with that. So with Q learning, so just going back to value-based reinforcement learning, with Q-learning you had this sort of the two choices, right? You've got choice number one of how you model the Q function. So choice number one is you model the Q function as basically state action pair comes in and out comes whatever I guess the return, something like that. And choice number two is to do it in a different way where you only input the state and out comes sort of a whole bunch of right.
But it just depends whether or not you have a what's your action space.
Yes.
Yeah,
Well,
I mean, if it's fixed, then the second one is okay.
Yeah.
Just for like Atari games. But the first one, like you cannot compute this return value for every single action when you drag a card, for example.
Exactly.
When you have just
so
that
that's,
angles of your wheels.
yeah. So that's true. I agree in principle. So the problem is basically this thing that's sitting here is some sort of function, and in the case of a discrete action space, it's a function from well basically Zn to whatever the reals, and in like let's say if you have like I don't know some continuous space, then you would have to have I mean I guess just the reals or Rn or whatever, and you map it to the reals again. Now the problem is, so this is very sort of compactly organizable in terms of just a vector of values.
Hang on, sorry, I'm trying to follow because you've got, this is, for the second one you're returning all the Q values for your different actions, right?
Yeah.
So why are you mapping from, is the state your multi-dimensional vector R or Z, and
so
then the single G function for each action is the result in the real, this the scalar result that you get back.
Yeah, so this is the values.
Yeah.
So let's say for each action that I can take, let's
Yeah.
say I take a specific action,
Yeah.
this just lives in the space of values, which is just a real number. Now, but depending on where A lives, this is a very different kind of mapping. So it's exactly what Dennis is saying. You either just put it all in a vector and then you just do a lookup in that vector, because that's basically what you're doing. You're taking the maximum over that.
Yeah.
Or you have to somehow analytically compute the argmax over a continuous space of actions, which is expensive to do. But now I was thinking, well, what if we just keep this structure, and instead of saying we cover the full space of actions, you just randomly sample a bunch of them, and then just calculate that.
How do you choose like which actions to sample from?
I mean, you just.
We're talking about continuous space now.
So you take, I don't know, like a Boltzmann policy from your from this, but the cool thing is that you can still do this off policy. So the cool thing is that you can still explore the values of all of these different of all of these different samples. So you know what?
So
You know
explore
what I mean?
action space as well as state space.
Well, so I would take, let's say, I would take, let's say, a batch of actions. Let's call it big A. And so it's basically just a bunch of samples. Right? I've just got n samples. Instead of having n categorical actions to pick from, I now have n samples. Then why wouldn't that work? So,
I'll just ask Stina to show you what we're doing.
Which your idea is to randomly sample from this action space, but isn't that like similar to just discretionizing the continuous space and then just...
yeah, that's so. Yes, kind of. So so if you take your space of actions, you could just like bucket it.
Yeah.
And then just draw a sample from each bucket. So you could do that, but you could also just imagine doing different kinds of discretization. So you could also just say, I have a space of actions. Let's say it's bounded, but I do have some sort of distribution over that space. So I want to use that information. So basically what I could do is just I kind of randomly sample a bunch of them. Something like that.
Yeah.
So then instead of having them all sort of equally spaced, so with this you're sure that you're exploring enough. With this you explore a little bit more in this region where you think you're already doing quite well. I think.
So this is not the space lowercase a is not the space of a single action. That's the space of all actions.
Of all actions.
Sampling
Yeah.
Okay.
Yeah. So this is basically the variable a, and this is the probability distribution over a.
Yeah. Oh, so you mean there are multiple probability distributions for multiple a's?
Yeah. So
A being an element of capital A.
Yeah, I guess. So what I would typically do is I would take, let's say, some sort of how would I wouldn't know exactly how to create a probability distribution.
How is that different from, say, Thompson sampling over the actions? I guess each state would be its own set of bandits, I suppose. That would be a bit messy.
Well, but you could, the thing is, you could draw different samples with every batch, so you don't have to take these things to always be the same.
Yeah.
So you can kind of continuously explore, but you could still do. So this is kind of this is how DQN works, right? It uses this kind of way where it just kind of evaluates everything all at once. Now the problem is that, of course, like if you only in the end, if you pick this one, this is the only one that you actually gather information about. It's the only thing that actually gives you some feedback. So this is the only output that you actually get to propagate your error back into the rest of the network. But so in this case, you could say like I'm somewhere here. So this gives me basically some sort of I don't know, like propensity or like log probability of my probability distribution that I have, and then I could just calculate. Sort of backpropagate through there, but for all those points, right? I think maybe not. I don't know. Maybe not. I haven't really thought of this through. But the idea being that instead of discretizing your space, you can do something sort of where you use the distribution of your action. Sorry. So
I'm trying to understand where you sample which. I'm sort of. I think I have a.
That gives me a probability distribution over. So and instead, let's say instead of mu, I would just use. What would you use actually? I don't know. I haven't thought of this. Sorry. I have to think about it more.
Yeah, I'm trying to understand where, because of course, if you follow regular sort of Q-learning, you have one action per state. You would just pick one action, however you would do that argument, or whichever way, out of your vector, or you would just get one return.
Yeah.
And so if I understand you correctly, you're trying to sample multiple actions from that vector to improve multiple values at once. for one, that sounds a little bit like sort of a Monte Carlo research-like approach, where you kind of guesstimate and then update with real values later. And the other would be, so you if I understand this correctly, then you would have you would keep the information that you've predicted, right? So it's not as an experience, but as a prediction replay buffer, so to speak. Yeah, and then that will populate your probability distribution. Is that what you mean?
No, I mean the thing that bothers me about the inability to do this is that in principle there's nothing really special about the categorical distribution. You should be able to do this with other distributions as well. That's the thing that I don't like about it. And then another thing that I feel like is sort of a bottleneck that we need to fix is that in like something like a soft actor critic, you evaluate this on a state action input, where this guy is actually drawn using the reparameterization trick. So it's basically so this is no longer a sample, but it's so it's basically mu of s plus epsilon times sigma of s, where epsilon is the thing that you sample from a distribution that doesn't have a parameter associated with it. So it's a reparameterization trick, like in and then so what you then do is that you take a single sample. So this could be anything, and it could be very far away. It could be a very atypical sample. Now, the problem is you only use one sample from this, and it would be nice if you could actually sample multiple things. So, so instead of sampling one epsilon, I sample, let's say, 100 epsilons, and then sort of the way to sort of do this more efficiently is to do it in this sort of type 2 way and not in the type 1 way. That's kind of what I'm thinking. But I don't really...
What would you backpropagate there, though? Because you haven't... There's no... Unless the counterfactuals are what I don't get beyond, because you would take only one action still. Yeah. So how would your estimation samples... Because there's no... You can't make a posterior of the multiple priors that you create.
But in a soft actor critic, do you, Patrick, in a soft actor critic, do you take the action that you put into the Q function, is that the thing that you actually take?
Don't well enough.
So in soft actor critic, you've got your actor that picks an action, and then you feed that into the Q function.
Yeah.
Is that action the thing that you actually drew? That you that you actually take? That you take to gather information about, say, the reward?
You use the min. It's two Q functions. You take the min of.
Okay, sorry, I haven't thought this through. I'll think about it more and come back, because I feel like
I
we're
might
getting a
be
bit lost.
wrong there.
Sorry for taking that.
No, it's okay.
I was just like, as I was cycling over here, I had this idea that I thought just would be nice.
Okay. So I don't know the dagger algorithm, so I'm not sure how difficult or unsurmountable or whatever that is. If I understand this correctly, for the first couple of things, you literally, like you said, you only run the given expert agent anyway.
So I got the version up and running.
you want to?
I don't know if I have a...
Do you have a USB-C?
No, this is old.
Oh, I think you've got one of those.
Old school. They're just warnings.
So this is the agent.
So what this is an expert policy. The other thing,
Probably here. Oh, you've got HDMI on.
no, that's a USB.
Oh.
The other thing was that I didn't have a Mijoku license, so I had to use RoboSchool.
Oh,
Just like
I see.
OpenAI version.
So the stuff that comes with OpenAI is not, because there are some open libraries or open something in the OpenAI stuff, but that's not good enough.
So yeah, this is a OpenAI gym environment. So
Yeah.
it's their version of the Mijoku engine.
Yeah.
So this is not Majoku itself.
It's OpenAI's.
Okay.
It's free.
Mm-hmm.
So anyway, what you do initially is so they give you some expert policies. You run the expert policies, record the observations and the actions. You don't actually record the rewards.
Yeah.
And then all that just gets recorded into one of these pickle files. And then literally all you do is train a supervised model on the observations, the input observations and then the output actions.
Yeah.
And then play it back and see the reward that it got.
Yeah.
So do they give you a hint as to like what the architecture for that thing should be?
Yeah, I just used
Just
where
feed
is it?
forward.
Yeah, I think I've got it here somewhere. just a couple layers, feed forward.
Right.
There was no science behind that. It was just like, yeah, as long as it has the right output shape. I just plotted some of these things. So blue is expert, green is the supervised.
This is the distribution of our actions?
Yeah, so this is a distribution of the rewards. So it ran, I'm having a bit of trouble remembering because I did this a couple of months ago. But so I think I ran each one like 20 times and just plotted the distribution of rewards that it got.
Yeah.
So it's actually, it's a very good copier.
Yeah.
Just like, you can sort of see.
Yeah.
But, and this was just something weird because you get more observations from the agents with more joints. You actually get more data, which is this is just me experimenting. And then the second part for Dagger was, the way I did it was just to run the supervised model again and record its observations and actions and then train on that, which is like, I don't think it's right.
So is Dagger just meant to be like a what's that called? I forgot the name. Cross entropy algorithm going. Is that called cross entropy? I can't remember.
So it stands for data set aggregation.
Oh,
so all you're doing is just adding additional data.
Oh, so you're not even filtering as to successful or not successful or anything.
So
you just add stuff.
I guess that was one of the
Yeah.
with an environment like this is like, where does the expert actually come from? Like you can't like label what's good actions for a given in observation or things like that. It's like
Yeah.
the robotics problem.
Yeah.
And so you kind of use the model to label for you, but it just ends up being like it's almost like circular in your.
But the idea is to slowly, I think it's to bootstrap the problem with expert data,
Yeah.
and then slowly feed in the experience that you generate.
Yeah.
So
But not too much, because then you're just completely chasing your own tail.
so for sort of moving out of sort of this kind of robot agent. So if you're trying to train a car, like you could record yourself driving, and then train supervised model on that, and then see where the model fails, and then train it, go collect more data on that situation, and then train that. And but often the problem comes with actually like labeling actions.
The interesting thing is, so you said that it only records observations, it doesn't record the rewards. So is the idea that the rewards and so on, like all the policies get shaped? But there isn't really an agent learning anyway, because you've just got a supervised system imitating.
Yeah.
So how are you ever going to exceed the original quality of it? That's just no.
And that's the other thing. How do you actually get beyond the expert? And that's where the dagger's meant to come in, which you can, if it's something that you can actually do better than your agent, then you can do the job and then label your actions and then train on that supervised data. But where do you actually get supervised data for this? Like, how would you even label like what the agent's meant to do in each situation?
Without a reward, though, how do you?
That's kind of the point.
Yeah.
It's meant to be like this is almost a motivation for like why you need to use RL.
Oh, okay.
Because.
So what are you learning? What's the mapping that you learn? You learn to map inputs to actions.
Yeah, observations to stats.
Yeah, but not rewards.
No, the rewards don't really go into
I see.
the project.
Okay.
The way I just interpret it is sort of this is why we need to do RL. This is why we can't just train supervised models to when you have to like actually take actions.
Yeah.
And that was very the thing he was talking about last week with the sort of tightrope. And each time step you make an error and you like fall off the tightrope. And so for example, if you're driving the car around, your model's not perfect. So at each time step, it can make an error. And if you make an error and it takes you into an area of the state space you've never seen, your model's more likely to make an error and end up in a worse and worse place.
Yeah.
And so if you just try to train in like a purely supervised way, it doesn't really matter because eventually, like as you take more and more time steps, eventually you're going to make a mistake, which puts you like off course, and you can never like get enough data to cover all the possibilities.
Yeah.
So it's almost like a motivating example.
I see. Interesting. So in terms of the second homework, what do they want to reuse from that first bit then?
So I don't know if this year's one was different, but the last year's one was just train a policy gradient to and first on car pole and then on these more complicated environments and see how it compares to just doing the supervised. They might have changed it, I'm not sure.
There's apparently there's code that's marked as to do get this from homework 1. So where you just copy code from homework 1 to do the plans. Could be that this is part of the regular code that they've got, but I'm not sure.
I'm not sure.
I also see that only half of us basically have laptops here. So would it make sense for us to watch a video, maybe an earlier video or a later video, and then do a proper coding session next week? Maybe with, I don't know if it would make sense for us to pre-download the repo or or something like that.
Look, I'm happy to do the coding session next week if everyone else wants to. Like,
Yeah.
Would that be?
Because I
Okay.
think
Yeah. Not that I want to postpone it or anything. It's just more that so we can definitely all.
Yeah.
Like,
I'll bring my laptop as well.
Yeah.
Same.
Cool.
I don't want to show you the code because I'm very anxious. I'm not a very good programmer.
Yep, I had a 1 hour code review yesterday. I hear you. Yeah. Cool. In that case, just if you just.
But yeah, the first project was just literally supervised learning.
Yeah. I remember in this Russian course that I did, this HSE Coursera course, they did a similar thing with the cross-entropy method, where you had no reward per se, but you just developed a sense for success, and then you just filtered, I think it was like distance covered, or I can't remember, and so you just selected your episodes that you kept in your replay buffer by success and so on. Yeah, it's kind of right. Now that's all. I was really happy when I found this. This is very, very cool. So, this is the episode I watched last week, and I think we rolled into the first minute or so of this one. So.
All right, let's get started.
All right, is that one? Because when I unplug this, it actually uses a TV too.
So, in the first part of this course, we covered a range of different model-free reinforcement learning algorithms. We talked about Shearing methods,
Should?
critic algorithms, value function-based methods. We learned that they're all actually quite
Maybe the volume of your laptop itself.
Should maybe.
better policy grading
Wait.
and so on. Now we're going to switch to talking about model-based reinforcement learning algorithms. And that'll cover about three. Today's lecture is going to be a little bit of a departure from what we usually do in this course. In today's lecture, we won't talk about any learning.
That was a lot longer last time.
Where is the toilet?
The toilet is straight through. You'll need my card to get back in.
Oh, sure.
So I got my key on the card. So
Thanks.
Just straight along, and then at the corridor, at the end of the corridor to the right.
Thanks.
Right. So.
What we'll talk about instead is optimization algorithms.
Well, the thing with that is, I'll try, but it's just not very loud.
In the setting,
I think it was last time when we did this.
no one actually learn anything. All you have to do is use your knowledge to make your optimal decisions.
Oh.
And then we'll use the stuff that we learned in today's lecture as a tool in subsequent sections where we talk about actually using learned models and then making optimal decisions with those learned models. So today's lecture is not about learning, it's about optimal control and planning. So it's a little bit of an aside to the course, but it's very useful stuff to know, because when you can learn your models, then you'll need to use some kind of optimal control and planning to actually utilize those models effectively for decision making.
Sure.
We can
All
start
right, a few logistical notes. So homework 3 is now out. It came out yesterday. For this one, I am serious. You really should start early. A long time ago, in the beginning of the course, we saw the algorithms, Monte Carlo tree search, and trajectory optimization methods based on linear quadratic regulators. The goals for today's lecture, there's really only one major goal, just to understand how we can perform planning and optimal control with known dynamics models in both discrete and continuous spaces. All right. So let's revisit something that we saw quite a long time ago. In the beginning of the course, we saw the reinforcement learning objective. And we talked about how in reinforcement learning, you have your policy by A given S or A given O. The policy receives a state, outputs an action. The world takes in that state and action and chooses the next state. And this defines a particular probabilistic model over trajectories, which factorizes a product of initial state distributions, policies, and transition probabilities. And for all the algorithms we've discussed so far, we basically assume that this bit is not known. It exists, the environment samples from this, but we don't know what it is, and we're not going to attempt to figure out what it is. We're just going to try to deal with the environment as sort of a black box sampler and figure out how to take good actions that result in high rewards. But we could also attempt to explicitly figure out what this thing is, essentially learn kind of what are the laws of physics that govern this world, and then somehow use that knowledge to make better decisions. So in model-free RL, we assume this is known and do not attempt to learn it. In model-based RL, we're going to try to learn it and then use it to make decisions. So what if we knew the transition dynamics? What if we basically knew this probability distribution? What could we do better than what we've seen so far? It's not that uncommon to have situations where you do actually know the transition dynamics. So if you're playing some kind of game, typically you actually know the rules to the game. Like the rules for playing chess are not secret, otherwise chess would be a much more complicated game than it is. You can actually write them down, you can implement them on the computer, and in principle you can utilize that knowledge to do a better job of making good decisions. Some systems are not actually known, but they're pretty easy to model. So if you're trying to navigate over a road network with a car, while it's true that some unpredictable things might happen, like maybe there's construction and the road is closed off or something, but at a high level you actually have a pretty good idea of how navigating through a road network works. That's how your GPS system on your phone can give you directions. So even though the true dynamics of the system are not known, it's pretty easy to model, and that model is decently accurate so you can use it. And then sometimes your goal is to explicitly make decisions in simulated virtual environments where the environment itself is implemented in a piece of code. So even though it might be a complicated piece of code, you have access to that piece of code, and you can exploit that to make better decisions. In other cases, you might not know the dynamics a priori, but they're not too difficult to learn. And learning dynamics ranges from kind of very simple methods to very complex methods. So in robotics, you might sometimes hear about something called system identification. System identification is essentially learning for roboticists. System identification is when you have some knowledge about your robot, like you know that your robot exists in our universe. It's affected by gravity and inertia, but there are some unknowns, like maybe you don't know how heavy it is or how long its links are. So system identification refers to identifying those unknown parameters. Now, that's in the case where you basically know the structure of the model. You can also use general purpose black box function approximators to learn models where you don't know anything about their structure, including big neural nets, and we'll talk about that later as well. But today, the main thing we're concerned about is, does knowing dynamics make things easier? So we'll come back to all these different ways in which we can learn dynamics. For now, we'll just assume somebody gives them to you. Maybe you're in this regime, number 1 or number 2, where it's pretty easy to model, or maybe you're in a simulated environment where you have access to the code that determines the behavior of the system. Whatever the case is, we'll assume that you know the dynamics for now, and just talk about what happens after that. Okay. So model-based reinforcement learning generally has the general kind of outline of learning the transition dynamics and then somehow using those transition dynamics to figure out how to choose your actions. So today we're going to talk about how you can choose dynamics under perfect knowledge of the system. And just to make sure that we're all on the same page, when I say dynamics, I mean this edge in the graphical model. So we saw this graphical model before. We have observations, actions, states. Don't be afraid if you see an X instead of an S. Remember from earlier on in the course, you can use X to denote state or S to denote state. You can use U to denote action or A to denote action. Oftentimes in optimal control, people use X for state and U for control. In reinforcement learning and dynamic programming, it's more common to use S for state and A for control. In this lecture, I'll switch back and forth between them a little bit, partly to keep you guys on your toes, and partly because in a lot of the optimal control literature, you'll see this notation more often. All right, so we'll talk about some optimal control, some trajectory optimization, and some planning and search algorithms. And then next week, we'll talk about how you can learn the unknown dynamics. All right, so before we saw this picture, when we talked about learning policies, so in this picture, there's some kind of input, something that you observe about the world that goes through your policy, and your policy outputs a distribution over actions. For most of today's lecture, we won't actually worry about policies. We'll be more concerned about just choosing good actions using models. So before, we saw that we could motivate an objective in terms of something that you'd like to happen in the world. So if you're taking actions in this situation, maybe you want to minimize the probability of being eaten by a tiger, or in general, minimize some cost, or maximize some reward. And of course, you can't choose whatever state you want. Your states are governed by some dynamics in the environment. And that's the thing that we're assuming is known for this lecture. So in some cases, this is actually fairly straightforward to think about, and there are going to be a few different cases that are mainly distinguished by whether the dynamics are deterministic or stochastic. So let's say that we have a deterministic setting. Deterministic means that the dynamics are a function. So you have f of SDAT, that gives you the next ST, and there's no randomness. In the deterministic case, things are fairly simple. You could imagine that your agent is going to look at what the first state in the environment is, the initial state, and then it's going to make a plan. And because the agent knows how the world works, and because the world is deterministic, it can make a plan, a sequence of actions, and then go and execute those actions, and it will do pretty well in that situation. So it receives a state, makes a plan, so that's what the thought bubble represents, and then it basically sends that plan off to the world and says, here's what I'm going to do. So the GPS system on your phone, you tell it I'm here, I want to go over there, it makes a plan for you, and then as long as you follow that plan, everything will be good. So mathematically, we can represent that as a constrained optimization problem. We'll see later on how we can turn it into an unconstrained optimization problem. So this is the constrained version of it. You want to maximize your reward just like before. Since everything is deterministic, there are no more expectations in this version. The expectations will come back shortly. But here there are no expectations. But there's a constraint that says that st plus 1, this is a typo, this should be an s, st plus 1 is equal to f of st at. Right, so the next state, you don't get to choose the next state, you only get to choose the action. The constraint forces you into the next state governed by your dynamics function f. All you get to choose is a sequence of actions a1 through a capital T. Okay, that's pretty simple. Now let's talk about what happens when you have stochastic dynamics. And now things are going to get a little complicated. So the first thing I'm going to talk about is where you're going to use the same general recipe. Your agent observes the initial state, makes a plan, and then goes to execute that plan. But now the dynamics are randomized, they're not deterministic. And we call this the stochastic open loop case, and you'll see what this loop is all about in a second. So in the stochastic open loop case, you have a distribution over states conditioned on your plan. Your plan is a sequence of actions. So you have P of S1 through capital T given A1 through capital T. And that is governed by a distribution. Now, since everything is conditioned on actions, the policy doesn't appear here. The actions are always on the right-hand side of the conditioning bar. But this is a complete joint distribution over state sequences given action sequences. And what you would like to do in the stochastic open loop case is maximize the expectation of your reward conditioned on your plan, conditioned on your sequence of actions. Okay, that's a very reasonable analog to what we had on the previous slide. Basically, the agent doesn't really do anything special in the face of stochastic dynamics, just does exactly what he was doing before, which is make a plan and then go and execute that plan. Can anybody think of what might go wrong here? Why might this kind of approach to choosing actions under stochastic dynamics be a really bad idea? Yeah. So the answer was you're planning under a false belief that at time step t you'll be in a particular place. It's not really a false belief. I mean, you do know what these probabilities are. Let me illustrate this with an example. Let's say that I'm going to tell you that at the end of today's lecture, I'm going to give you a quiz, a written quiz. It's a multiple choice quiz with 5 questions. Each one has 4 possible answers. And I'm going to ask you to do this. I'm going to ask you to make a plan. I'll even tell you what the quiz is about. It's going to be an algebra quiz. But I want you to tell me what answers you're going to fill in. 5 questions, 4 answers each. Yes? Right, you can't really figure out what to do because you haven't seen what the quiz is. You haven't actually observed the outcomes of those actions. So even if you have a perfect model, even if I tell you, 30% chance question 1 will be, solve for x where x plus 1 equals 2 or something, and 30% chance that it'll be x plus 1 equals 3, you know exactly what the possible questions will be, what their distribution is. We don't know which particular one I'll give you, so you can't tell me what the answer is. Right? Because under stochastic dynamics, you actually gain information every time step. Every time step, some state is actually sampled from that distribution, and you get to see that state. But if you have to make a plan in advance before having seen it, it's very difficult to make a good plan in some cases, just like it's very difficult for you to tell me what answers you'll fill in for that quiz until you actually see what the quiz is. So, yes? Right, so the question was, do we see a similar issue in the deterministic case if you only have observations about the world? And the answer is generally yes. There are some caveats, which is, your observations might tell you everything you need to know to choose the right action. So you can construct kind of partially observed settings where future observations will actually tell you something about what state you were in the past. That's pretty reasonable, right? So if I don't know which room I'm in because I'm staring at a blank wall, I turn around, I see the rest of the room, I now suddenly know where I was a second ago. So in those settings, yeah, the same basic principle can apply. Other questions? Right. So this is suboptimal. And what do I mean by loop? Well, when you hear the term closed loop, that means that the process by which the agent makes decisions involves feedback. So the agent observes the state of the world, takes an action, or typically according to some policy, and that's the loop. So every single time step, it goes around this loop. When someone says open loop, what they mean is the loop is not closed, meaning this arrow at the bottom is missing. So in open loop, typically what that means is that the agent observes the initial state or some kind of initial piece of information, and then produces a complete plan, closes its eyes, and then blindly follows that plan for the rest of the episode. So the open loop case can be highly suboptimal in the stochastic setting, but of course not in all stochastic settings. So maybe you have just a little bit of randomness, in which case maybe it's not so bad. So in general, it can be very bad. In specific cases, it might often not be so bad. Okay. So you could, of course, have the stochastic closed loop case. The stochastic closed loop case refers to the setting where the agent observes something about the world, and then doesn't make just a single plan, but makes kind of a plan with contingencies, if you will, which is essentially a policy. So a policy is just a plan for all the possible things that might happen. It doesn't say, I'll take these actions. It says, if this happens, I'll do that. If this other thing happens, I'll do this. And that's what a policy is. So the stochastic closed loop case, your trajectory distribution is the familiar thing that we've seen before, and your planning now corresponds to figuring out the best policy. Now, of course, we've seen that policies can be represented by complicated things like deep neural nets, but you can also represent policies in simpler ways. So a policy could, for example, be a plan with contingencies that's local to the particular trajectory you intend to execute. So a neural net is a very global kind of policy. You could imagine for some continuous systems, like for example, if you're controlling an airplane that's trying to follow some trajectory, you might have a very simple policy that's still closed loop, but doesn't have a very complex functional form. Like for example, a time-varying linear policy. So a time-varying linear policy, intuitively you can think of it as an open loop course of action with a little bit of feedback to stabilize it around a particular desired state. So that's a very simple class of closed loop policies. And there are many, many other choices. In fact, a closed loop policy in a discrete space could simply be something like a decision tree. You could say, if I got into this state, I take this action. If I got into this other state, I take this other action. So you can have a very wide range of policies ranging from very powerful, very global things like neural nets to very weak, very local things like time-varying linear controllers in continuous spaces. All right. But first, we'll do some open loop planning. We'll start with open loop planning because it's really simple. And you'll actually implement open loop planning for homework 4, for the homework on model-based RL. So open loop planning in the deterministic setting is totally fine. In the stochastic setting, it can be quite suboptimal. But we can do it anyway because it's so simple. So the first class of methods that we'll discuss for open loop planning is stochastic optimization methods. So these are essentially black box optimization techniques. They don't really care that you're doing control or planning. They're just optimizing some objective. So we're going to abstract away our optimal control or planning problem. The problem consists of maximizing some objective with respect to a sequence of actions. We don't really particularly care what objective that is. We'll just call it J, and we'll just say our sequence of actions, A1 through A capital T, is capital A. It happens to consist of a bunch of time steps, but for the purpose of this discussion, we don't actually care about that. So as far as we're concerned here, it's just a big long vector of numbers with, if you have D dimensions in your action, it's D dimensions for every time step. So if you have T time step, it's D times T in size. So a big long vector of numbers, maximizing some objective. That's basically the problem. And I would say any optimization method can be used for this. It's just that because of the particular conditions under which we tend to use model-based reinforcement learning, some optimizers are better than others. You can use, for example, first-order gradient descent. I'll discuss later why that's not a very good idea. For now, I'll actually talk about derivative-free methods. Derivative-free methods are very appealing because in many cases, you might actually have a model of the dynamics that you can evaluate for any sequence of actions, but it's quite hard to differentiate through. So for example, if you're controlling a simulated robot in the Majoku simulator that you use for homework 1, it's pretty easy to try out what happens if you take different sequences of actions. It's comparatively quite a bit more difficult and numerically expensive to calculate derivatives through that simulator. So it'd be quite nice if we can optimize this without derivatives. So the simplest method for doing this is actually, in some ways, the most obvious. You basically just try out a few random sequences of actions and see how well they work. So you might sample a bunch of action sequences, capital A1 through capital AN, from some distribution, maybe a uniform distribution over all valid actions, and then choose the one that gets the best score. Not necessarily a great optimization method, it's just random sampling. But it's very parallelizable. You can check all these action sequences in parallel, and if you have a very short horizon, meaning capital T is small, and the dimensionality of the action is small, you can get kind of a decent answer from this. But not a very good answer. And we can actually do a lot better than this kind of guess and check method. This is sometimes referred to as random shooting in controls. Any questions about this? Okay. So now let's talk about how we can do a bit better. So one popular approach for doing derivative-free optimization that is structurally very similar to this kooky technique I had on this slide is to basically do the same thing but multiple times. So in the cross-entropy method, you pick your sequence of actions, you pick n sequences of actions randomly from some distribution, and then you could choose the best one, but the way that you can do better is instead of choosing the best one right away, you actually modify your distribution. So the idea is this, that let's say the vertical axis here is my objective, the horizontal axis is my action sequence projected onto 1D so that I can visualize it, and let's say I generated 4 samples, and these are the samples I got. Now, if I get to go again, if I get to basically generate some more samples after this and iterate, one might imagine that it would be much better to generate kind of more samples in this region where I have some good stuff and not waste my time generating more samples over here where I didn't see any good stuff. So what I can do is, instead of sampling again from the uniform distribution, I can fit a distribution to only the good samples and then sample from that. So that'll give me more samples in the good region. And then I can do this process again. I can take the best of the samples that I got, the best of the green ones, fit another distribution to that, and sample some more there. And if I do this repeatedly, I'll get better and better samples, and that will in practice give me a much better optimum for my objective J of A than if I would just use those random samples from the first iteration. So the cross-entropy method basically works like this. You sample from some distribution. Maybe initially this could be a uniform distribution over all valid values. Then you evaluate the objective value for all of those. Then you pick what are called the elites. So the top m of your samples. So you choose some number m less than n. The top 10% works pretty well if you just want a number. So you pick some number of m less than n, choose just those elites, and then you fit your distribution to just the elites. So in my example up here, I have 4 samples and 2 elites. In practice, you might have more like 128 samples and maybe 32 elites. And then you just repeat this process. For continuous valued actions, a multivariate normal distribution works quite well, but you can really use any parametric distribution class for this. So the nice thing about the cross-entropy method, it's not actually a particularly good optimizer, but it's really, really simple. It's very quick to code up. And it's quite easy to parallelize, because all these evaluations in step 2, those can all be done in parallel. And typically it's step 2 that's the most expensive, because step 2 is where you use your model. So step 2 is where you use your model to figure out which states you will get from taking those actions and what the reward of those states is. If you have a big neural network dynamics model, then step 2 basically amounts to running your neural network many times. So that's where most of your computational cost comes from. Okay, does anybody have any questions about the cross-entropy method? Okay. So that's something that we can use to very quickly code up a little optimizer that we can utilize even when we can't compute derivatives through our model, and we can use it to get good action sequences. This kind of stuff tends to work decently well when the total dimensionality of your problem is on the order is like 64 or less, let's say. If it gets up to 100, that's kind of pushing it. If it's more than 100, it's probably not going to work. So if you have a relatively low dimensional system and or a small number of time steps, this kind of stuff can actually work pretty well. If it's higher dimensional, this will start to really suffer. Okay. If you want to find out about fancier versions of these types of algorithms, you can make this much fancier. So if you look up something called CMAES, covariance matrix adaptation, that's kind of like cross-entropy method but with momentum. So it doesn't just fit the latest elites, it sort of figures out which way you've been going and pushes you along that way. So if you want a much fancier version of this, you can look this up. But if you want something really simple, then you can just go with the standard cross-entropy method. Yes? This one, yeah. Right. So is that your comment? Okay. Yeah. So for those of you that didn't hear, the picture looks suspiciously similar to a picture I showed before when I discussed how policy gradient has high variance, and I use that to motivate why we need to subtract a baseline. And now suddenly this is not a problem anymore. Why is it not a problem? Well, it's not a problem because we're not actually using the numerical value of the reward. We're just sorting them based on the reward and picking the top m, and then those top m all get the same weight. We don't actually care which of these top m is better. The actual numerical value of the reward is not used for the fit here. Now, those of you that are kind of thinking about connections between these might at this point wonder, well, it seems like there are a couple of things that changed, right? We're taking the top m, and now we're fitting these distributions, so what if we kind of mix and match a little bit? What if we don't take the top m? What if we somehow use the numerical value of the reward and weight the samples? You can actually do that. You can have a soft version of CEM, where instead of just taking the top m numbers, or top m vectors, you actually weight all of them by some positive function of their reward, so that the good ones get a larger weight. That's a perfectly reasonable thing to do. It has a few more hyperparameters because you have to decide what positive transformation of the reward to use, but it's a valid method. Another thing that some of you might be thinking about is, well, why don't we import this trick into policy gradient? So can we do policy gradient with kind of a top m style rule? And you actually can. It's a little bit weird to explain mathematically what that does, but you can actually design algorithms that work on that principle, where you do policy gradient instead of grad log pi times r, it's grad log pi times some function of r. You can actually get that to work decently well. So those of you that are interested in this, you could look up an algorithm called reward-weighted regression, which operates on this principle. It's a decent algorithm. I think it's not quite as good in many cases as regular policy gradient, but it has some interesting mathematical properties. Yes? The question was, is this assuming that there's a single state? No, this is not assuming that there's a single state. So capital A here, there's a little bit of confusion because I use subscripts to mean slightly different things. So capital A is an entire sequence of actions. So capital A is a big long vector where it's A1, then A2, then A3, then A4, then A5. When I use subscripts 1 through n here, I'm just referring to different samples, not different time steps. Yeah. So the way that you evaluate J is you actually take that sequence of actions, predict which states you will get, so actually you run it through your model to get S1, S2, S3, S4, evaluate the rewards, sum them together, and that gives you J. Yes? I have a question back there. Why is the name called cross-entropy method? It's a somewhat complicated story, but maybe this one is better to take offline. Yes. Where are we using the model? Yeah. So we're using the model to evaluate J. So just to make this very explicit, J of A is equal to the sum over T from 1 to capital T of R ST AT, where ST plus 1 is equal to F of ST comma AT. So the model is used right here. So, you know, I've written this out as this kind of funny constraint thing. We can just substitute that in there, and then you get R of S1 comma A1 plus R of F of S1 comma A1 comma A2 plus R of F of, you see where I'm going with this, comma A2, comma A3, etc. Now, writing this out takes a very long time, and I do not have a big enough whiteboard for it, but if I had a really big whiteboard, I could write this out all the way to capital T, and that would be the unconstrained optimization objective. Any other questions? Okay. All right, so what's the good thing about this? It's very fast if you parallelize it. It's extremely simple to code up, which is a virtue that should not be underestimated. What's the problem? Very harsh dimensionality limit, so 50 and above gets kind of tough, 100 and above, pretty much hopeless. And it only does open loop planning, so this won't allow you to solve my algebra quiz. All right, let's talk about another method that handles the stochastic case a little bit more gracefully. So the next thing that I'm going to describe is something called Monte Carlo tree search. Monte Carlo tree search tries to construct...
Hang on. I thought open loop planning was the algebra quiz and closed loop planning was the decision tree basically for a discrete case.
No, he's saying if he said he was going to give you an algebra quiz,
Yeah.
and you had to plan out the answer you're going to give right now without knowing what the question is.
Yeah.
You couldn't use open loop planning.
Yeah.
Yeah.
Oh, sorry. Yes. Yes.
plans, it works in both continuous and discrete action spaces, but it's really much easier to use in discrete action spaces. And it can be used to plan through stochastic systems. In fact, Monte Carlo tree search has been very popular for calculating plans to play stochastic games because it handles stochasticity quite well. So here's the high-level idea. Let's say that we'd like to play some Atari game, like Sequest. I think Sequest is actually a pretty fun game. You get to shoot a bunch of fish for some reason. Not very ecologically minded. So let's say that you'd like to play Sequest, and you have the Atari emulator, and you can reset that emulator to any state you want. So if you'd like to see in a particular state whether shooting the torpedo versus surfacing for air is better, you can surface for air, see what reward you get, then reset back to that state, and then try shooting the torpedo and see which of those led to better outcomes. The problem is that you have to make a decision every single time step. So the number of possible plans is huge. So you could imagine, you start off in state 1, let's try action 1, or sorry, let's try setting action time step 1 to 0, see where we get to some state 2. When you see me use a subscript here, keep in mind, S2 is not referring to the second state in the system, it's referring to the second time step. So if I take action 1 equals 1, I get also an S2, but now it might have a different value. And something very important to keep in mind, this is a stochastic system. So taking action A1 equals 0 multiple times might lead to a different state. So when you see me draw a tree like this, each node in the tree doesn't necessarily correspond to a single unique state. It just corresponds to the outcomes that you get from taking that action. So taking action A1 equals 0 just once might not actually be enough to understand if it's a good action, because it might have a stochastic outcome. But even before we worry about that, let's say that it's all deterministic. I can take action 0, I can take action 1, they have two possible outcomes. Okay? In each of those outcomes, I can also take action 0 and action 1, so then I get 4 possible outcomes. At the next level, I'll have 8, then 16, and then 32, and before we know it, you have more possible outcomes than there are atoms in the universe. So what can we do? Well, one thing that we might consider is that really we don't need to expand this tree all the way to the end of the game, because perhaps all we really need to figure out is shooting torpedo better than surfacing for air? So if you shoot the torpedo, maybe you kill the fish and you get a point. If you surface for air, then you don't kill the fish and you don't get a point. And maybe you have enough air already, so surfacing for air is useless. Perhaps it's okay to just expand this tree for a short while, and then, at the end of that short expansion, play out some kind of default policy to the end of the game, just to see if you put yourself in a better place or not. So, perhaps one of the ways that you could approximate the full value of some actions up here is by playing out the game up to some depth, and then at that depth, just do something that allows you to finish the game and get a score. The intuition is that if even a simple, maybe random policy leads to a good outcome, then perhaps the actions you took to get there were pretty good actions. So maybe you have some default policy, I, AT given ST, and you just play out that default policy from the leaves and that allows you to essentially finish the game and get a number. It's not a great way to get a number, but it's okay. Like if you imagine playing chess, maybe you're at the end of the chess game, you manage to check your opponent, and then you do something random. If even doing random stuff leads you to win the game, well, then whatever you just did must have been a really good move. Yes? Yeah. So the question is, can we do better than just playing some stupid random policy? Can you, for example, learn a neural net that gives you better values here? The answer is you can. In fact, there's a million different improvements you can make to MCTS, and I'll mention some of those towards the end. Yeah, so that's basically the intuition, that you can play some fairly unintelligent policy at the leaves, get an estimate of your value, and that can tell you roughly which of the actions up here were better or worse actions. But now let's try to instantiate this intuition in a practical algorithm that we can actually code up. So one of the things we have to decide is, we can't really search all the paths, so where should we search first? So for example, maybe you took some action a1 equals 1 here, and then you like died and the game ended and you got a really bad score. It's probably not worthwhile to keep trying this again, because the other path is probably more promising. So you can do a lot better than just expanding the tree in a balanced way. You can expand it in a way that preferentially puts more samples into the regions that seem to be resulting in good outcomes. So you have to decide where to search first. So maybe you took action a1 equals 0, and you got a score of plus 10 after running your random policy from that state. So plus 10 is the score of the entire trajectory that results from taking action 0 first and then doing some random stuff. And then you try taking action 1 and then doing some random stuff, and you got plus 15. So now, intuitively, it kind of seems like if you had to choose, if you had like one more sample left, maybe you're better off trying to go here and see what the second action that's good to take here would be, instead of going here and trying the plus 10. Because it seems like the plus 15 thing is likely a little bit better. It's certainly not guaranteed to be better, because it could be that what you did is you took a really good action and then your random policy did some really stupid stuff, and maybe there's some other thing you could have done here that would have gotten you a plus 100. But in the absence of any other information, it kind of seems reasonable to conclude that action 1 is probably a little bit better. Okay. So the intuition, choose nodes that have better reward, but don't just abandon the nodes that had suboptimal reward, because maybe you could have done something else downstream and gotten a better reward. So instead of just greedily choosing the best one, you should choose the best one, but also sometimes retry some of the others, especially if they were visited very rarely before. So here's a generic sketch of a Monte Carlo tree search algorithm. At every iteration of the algorithm, we're going to expand one node. And the way that we do this is we find a leaf, SL, using what we call our tree policy. The tree policy is not really a policy, it's just a strategy for selecting which leaf to expand. Then we're going to evaluate that leaf using the default policy. The default policy is actually a policy, that's literally something that you run out until the end of the game. And then step 3, we're going to update all the values in the tree between our root and the leaf that we expanded. And there are different choices we can make for the tree policy and for the default policy that will affect how well this algorithm works. But then at the end, when you're done, you take the best action from your root, which is the action that leads to the node with the highest value, and then typically you would repeat the whole process. All right, so let's say that we selected action a1 equals 0, we got into some state at time step 2, that's S2, and then we ran our default policy, and we got a score of 10. What we're going to store in this node is a value, which I'm going to denote as capital Q, and a number of times that we visited that node. So we visited that node once, so n equals 1, and we got a score of 10, so Q equals 10. And then I'm going to take the other action, because I've never taken that other action before. Who knows, maybe there's a pot of gold at the end of that action, so I want to try that one out too and see where that leads. And maybe I'll get a value of 12. And remember that 12 is the sum of all the rewards on this edge plus what I get from running my default policy. So I get 12. And I store n equals 1 because I only visited that once. So now, I have to make a choice. I have to do step 1. I have to find a leaf using my tree policy. Which one do I pick? Well, I have two choices. They've both been visited once, so they're both equally rare. And one has a score of 10, the other has a score of 12. So here the choice is pretty clear. I'm going to go with the 12 because they're both equally rare, but the 12 is a better number. So I'll go there, and I'll expand. Here's how we can formulate the tree policy. If a particular leaf is not fully expanded, you choose a new action. Now, not fully expanded means that there are actions that you've never taken before. That makes a lot of sense because if you've never taken an action before, if you've taken it 0 times, who knows, maybe that's like a really incredibly good action. So if you arrive at a leaf and there's actions that you've never taken, just take one of the new actions because you don't know anything else about it. However, if all of the actions have been expanded, like they have at the root here, then you choose the child with the best score. And the design of the score is basically what's going to determine how well this MCDS method works. So I said before that the intuition is something like choose nodes with high value, but also choose nodes that haven't been visited too often. So that's why After we've expanded 0 and 1 and we're sitting at the root, we're probably going to go to 1 because it has a better score and they both have the same frequency. Once we arrive at S2, then it's not fully expanded, so we're just going to choose a new action. So once we arrive at this node, the choice is easy. It has unexpanded action, so we choose some new action. So we chose action A2 equals 0, and perhaps when we ran this, we got a total score of 10. Now, important not to get confused by this. This 10 doesn't mean that you got a reward of 10 for this one step. That means that after you did this and ran your default policy, the total score was 10. So this is the score of an entire trajectory. And you visited this node once, so n equals 1. Now, remember step 3, update all values in the tree between S1 and SL. So this is SL, this is the thing we just expanded. We need to update all the other values on the path to the root, which means we need to update this one. How do we update it? Well, we just add these things to that. So this becomes a 22 and this becomes a 2. So we add together the scores. So what that means is that we've been to this node once, got a score of 10. We've been to this node twice, and the total score added over all the times we've been there is 22. The average one is 11. So now this node has an average value of 11. This has an average value of 10. Okay? What happens next? Now we have, we're going to start again. We're going to start at the root. We have an important choice to make. We have two places we could go. We could go left, q equals 10, n equals 1. Or we could go right, q equals 22, n equals 2. Now the average value of that right node is 11, 22 over 2. 11 is bigger than 10, but it also has been visited more times. So we might say, well, the right node is only a little bit better. The left node has been visited less often. Maybe here we'd rather go to the less visited node because it's been visited 2 times less often and has a pretty similar score. So even though it's a lower score, we might still want to go there. So the particular function that we might want to use for choosing the child, the score function, there are a few different choices, and it's a little bit of a design choice. A very popular choice is something based on the upper confidence bound heuristic, which is a very good rule for exploration. That's to choose the score according to the average value, so q divided by n, plus a little bonus for nodes that haven't been visited very often. And let's unpack the equation that I have to get this bonus. In the numerator, this is the logarithm of the number of times that the parent has been visited. So for the root, that's just the number of iterations. And in the denominator is the number of times that the child has been visited. So if you have a child that's been visited once, and the parent has been visited 1,000,000 times, then the log of 1,000,000 divided by 1 is a decently large number. If the child has been visited 900,000 times, the log of 1,000,000 divided by 900,000 is a pretty small number. So that child is going to get a really small bonus, and it'll be mostly dominated by its score. And then the constant c here is just a number that you choose that determines how much you prefer to prioritize exploring new nodes over exploiting the ones that you've been to before. Now, there are many other choices for these kinds of exploration bonuses, and I'll show you some references at the end of the section where you can read more about that. Okay, so in this case, if we actually evaluate the score, we'll find that the right node actually has a larger score value, even though it has a slightly lower average value if you divide q by n. Sorry, I meant the left node. The left node has a larger score. So we go to the left node, and then once we go to the left node, now the first rule kicks in because it's not fully expanded, so we choose a new action arbitrarily. And then that action, maybe the total score for the trajectory that we got was 12, n equals 1. We have to go back up to the root and update the values, which means that we update this one by adding the n and the q. So that one now also has a q of 22 and an n of 2. So now when we go to choose, at the root they're both about equal, so we choose arbitrarily, and then both of those children have unexpanded actions, so there we don't have to look at any scores, we just expand a new action. Maybe we expand this one, we get an 8, so now we have 30 at that node, and n equals 3, and so on. And this process continues until we exhaust our computational logic. Okay, so that's the Monte Carlo tree search algorithm. Does anybody have any questions about this? Yes? Right, so the question was, how does all this depend on the default policy? Well, it depends on the default policy very much, because if you have a really, really smart default policy, that'll give you a pretty good estimate for the values that you get if you were to actually play smartly. If you have a really silly policy, you might get poorer estimates. In practice, for some reason, people really like to do Monte Carlo tree search with random policies, probably because they're so simple to use. In practice, of course, you can get it to do better if you use maybe a really smart learned policy. But for small action spaces, you can actually use random policies and get pretty decent answers out of these things. Any other questions? Okay. Yes, over there. Right. So the question was, it sort of seems a little funny, like you're using Monte Carlo tree search to find better actions, but if you already have better actions, then you'll get even better actions. Yes. So you could actually imagine using Monte Carlo tree search in the loop where you actually run Monte Carlo tree search, somehow use it to update your policy. Maybe you regress onto the good actions that you took up here, then use that policy as your default policy, do some more search and repeat. That's actually a pretty good strategy, so that's how AlphaGo works. Yes. How would you do this if you have continuous actions? So if you have continuous actions, then you have to change this rule. This rule says if ST is not fully expanded, you choose a new action. In continuous action space, there are infinitely many actions, so you have to change that up somehow so that you actually keep going even though there have been actions that you haven't taken before. And there are many, many different ways to do that. Some of the citations I'll have in the next slide discuss that a bit. All right. So if you want to learn more about Monte Carlo tree search, this is a survey of MCTS methods and a basic summary of the overall structure of the algorithm. This is probably what I would recommend as a starting point, and then you can read that survey and then follow some of the citations there for more detailed discussion on each individual topic. A little bit of a kind of a case study of some work that has used MCTS in a deep RL context. This is a paper that's probably about 6 years old at this point. So in this paper, what the authors did is they actually used Monte Carlo tree search to play Atari games, and then they trained a deep neural network to basically copy the behavior of the Monte Carlo tree search. So it's not an RL algorithm of the sort that we've learned about before. It's actually an algorithm that kind of combines Monte Carlo tree search and imitation learning. And the particular imitation learning method they use is actually Dagger. So in Dagger, if you recall, you have to label the states that your policy visited with optimal actions. In an imitation learning setting, you would have a person actually do this. Here they used Monte Carlo tree search to construct those labels. So using Dagger, which hopefully all of you guys remember from before. All right, at this point, I'll take a 2-minute break. So I'll be back when that clock says 11:05, and then we'll discuss optimal control in continuous space and LQR in the last portion of the lecture.
Do actually leave the camera running during that 2-minute break?
I think so, yeah.
Whereas MCTS really excels when you have.
Anyone, any questions, anything unclear? Because we've got to Monte Carlo tree search already. So,
Yeah, we could have already talked about it.
it was the last exercise in that course as well, in that Russian reinforcement learning course.
Okay.
The very last exercises.
Were they the ones who also said that AlphaGo was like the most overhyped
Yeah,
application of
they're,
reinforcement learning?
yeah. They are not taking themselves and the whole field not very seriously. So, yeah.
I'm just gonna get another drink. It's okay. Why do you even push this lecture?
Because half of you don't have your laptops with you, and when we looked at the homework, we have to download, we have to clone the repo, and then there's not much point in you looking over my shoulder watching me type. So we're doing this next time. I'm gonna bring the laptops next time, and I'll make sure.
So you see all of us like working
Exactly.
independently.
Yeah. Well, basically, so that way you can take it home, right? Because otherwise, if we do what Chris did that one time when we had the Collocation session, then sure we can share this, but there's not much point because that would be more like, I guess, a lecture or showing code, and that's not.
I see what you mean.
Yeah, I don't think that's a useful session.
Stochastic problem. So it's not about whether you have destination, it's about whether you get to choose the transitions deterministically or whether you choose actions and get a random transition. So for like some examples of places where people have used MCTS before are like playing games of chance like poker. So you can't really use A* search to plan through poker because you don't know what your opponent is going to do. But in a simulator and use MCTS. No? You can actually use any parametric distribution class you want for cross-entropy method. The Gaussian distribution is the simplest one to use, but anything that you can fit quickly and sample from will do the job. So if you have, for example, a bounded interval, you can use like the beta distribution, and that will work.
Very optimistic 2 minutes.
Right, so you probably just look it up in a textbook. All right, let's continue. So in the last portion of today's lecture, I'm going to talk about optimal control algorithms that, unlike the methods we've talked about so far, actually use calculus and use derivatives. So sometimes derivatives are very hard to come by. For example, if you're playing Atari games.
So that was Charlton Heston? No?
No, I think probably one of them would be Bellman.
Oh, okay. Looks a bit like Charlton Heston.
And you're using the Atari emulator, that doesn't give you derivatives. But sometimes you can actually get derivatives. Maybe you can write down the physics equations that govern your system. Maybe you have a robot, and that robot is governed by known laws of physics. You write them down. You take the derivatives, maybe manually or maybe using automatic differentiation. It seems like it'd be awfully nice to use those derivatives. And again, don't be alarmed. this is this, and this is this. And I'm going to use X's and U's for all of this because this is going to be optimal control stuff, and this is what optimal control folks like to do. But don't worry about it. All right, so if we want to talk about using derivatives, we're going to start by dealing with deterministic dynamics here. We'll actually introduce stochasticity later as well, and we'll see how for very specific classes of stochasticity, very specific distributions, the same ideas can still work. But for now, let's not worry about it. Let's say everything is deterministic, which means that the problem you're solving is to maximize the total reward or minimize the total cost with respect to your actions, where the next state is given by f of the current state in action. Now, as I wrote on the board before, this constrained optimization problem can be turned into an unconstrained problem simply by substituting in the definition for xt. You have to kind of substitute in recursively because x3 depends on x2, which depends on x1. So writing that out results in this really, really messy formula. This is what we actually want to do, but I'll write it out in a constrained form most of the time, simply because it's such a pain to write all these nested f's. But just keep in mind that if you see an equality constraint, it's pretty easy to substitute that equality constraint to the objective and get an unconstrained objective. So it's that unconstrained objective we're going to be dealing with. And now you might say, well, I have an optimization problem. It is unconstrained. All of the functions in that optimization problem are known. They're all differentiable. So why don't we differentiate via backpropagation and optimize using gradient descent? That's pretty straightforward. We all know how to do gradient descent. All we need is df dx, df du, dc dx, and dc du. So if we have all those things, gradient descent seems like it ought to do the job. Now, you can actually do that in some cases, but in many cases for more complex optimal control problems, that's actually not a good way to solve this particular optimization. So in practice, it really helps to have a more powerful optimization method, such as a second order method. Let me provide a little bit of intuition for why that's true. So the particular optimization I had on the previous slide is something called a shooting method. It's called a shooting method because you're optimizing over actions, and the states are the consequences of those actions. So you can sort of imagine that you choose those actions, and then you run your dynamics forward, you sort of shoot them outward, and see which states they hit. And what that means is that if this is your trajectory, horizontal axis time, vertical axis state, small changes to the action in the beginning will lead to large changes in the state at the end. Right? So it'll wiggle a lot. Right? Imagine holding a really long ruler in your hand. You move your wrist a little bit, the tip of the ruler moves quite a lot. And numerically, this is very bad news because it means that if you actually consider let's say the Hessian for this problem, it might be very ill-conditioned. You might be extremely sensitive to some parameters and extremely insensitive to others. So this in practice means that shooting methods, or optimization problems corresponding to shooting methods like this one, are quite difficult to solve with first-order optimizers like gradient descent. Typically, they will actually get stuck because of poor conditioning. There is an alternative which is called the collocation method. We won't talk about collocation methods too much in this course, but I just wanted to introduce the term so that you guys are aware of it. If you hear somebody say, I'm not using a shooting method, I'm using a collocation method, because I'm cooler than you are, what they really mean is that they're optimizing over states, and they're enforcing this constraint. So in a collocation method, instead of optimizing over actions and letting the states be a consequence of that, you actually optimize over states and actions, and then enforce this constraint, typically in some approximate way, typically by linearizing it. So there you would actually move the individual states around, which typically results in a much better conditioned optimization problem at the cost of having to somehow enforce this constraint. We're not going to talk about that too much, but if you're curious about this, typically what people use is some variant of sequential quadratic programming, where they locally linearize the constraint, make a second-order Taylor approximation of the cost, solve a quadratic program, and then repeat. So that's collocation methods. But what we'll talk about is shooting methods, where instead of doing regular gradient descent, we'll actually introduce an algorithm that does a kind of a second-order Newton's method style way of optimizing it without ever having to build the full Hessian. So for Newton's method, it tends to be very expensive in high dimensions. You have to build this Hessian matrix. But if you're doing optimal control, there's a very convenient way to avoid having to build the full Hessian. So to derive this, we'll actually start with a much simpler control problem called a linear quadratic regulator. This is a control problem where you're trying to minimize the cost just like before, but your f has a very special structure. So instead of having some arbitrary function f, we're going to assume that f is a linear function of x and u. So what I have here is a general form for a linear function of x and u, some matrix capital F times x and u plus some vector little f. And in general, you might have a different matrix and vector at every time step. We'll see why that might be useful later on. Okay? So we have linear dynamics. And we'll also assume... Sorry?
F is dynamics, right?
Yeah.
So and x is, x is a state and u is an
x. Yeah.
That's right.
Mm-hmm. Yeah. So you would consider f a model?
Model dynamics, yeah.
Yeah.
Okay. Their cost is quadratic.
Sorry? Oh.
You.
Yeah, yeah.
do you? What? Sorry.
F is like P.
We're just trying to
Oh,
make
yeah,
sense
right.
of
Yeah.
Yeah.
optimal control notation.
Yeah.
Yeah, that's what translation.
And C is R, basically, or minus R actually.
Cost?
Yeah.
Yeah. But negative.
So
I mean, opposite.
quadratic means that there is some linear component and there's some matrix component. There's also some constant that gets added, but we don't care about the constant because the constant isn't going to affect our actions. So when I write cost, I will not actually write any constant, even though you could have one, because it's not going to change the answer. So the cost is fully determined by a matrix capital C and a vector little c at every time step. Okay. So that's the sum. Linear dynamics, quadratic cost. We'll see how to go to the more general case a little bit later. All right, linear and quadratic. That's why it's called linear quadratic regulator. So that goes to the F, and this goes to the C. All right, so here's what we've got. We've got our quadratic cost and our linear dynamics. And what we're going to do is we're going to try to figure out what is the best action to take at the very end. The last action, U capital T, affects only one term in that sum, the last one. So figuring out U capital T is probably a little bit easier than figuring out everything else. So let's solve for UT only. This is the only term that depends on that. Now, the cost here depends on UT and it also depends on X capital T, which is unknown right now. It's, well, you know it, but it's some really, really complicated function of these F's. So let's not worry about what X capital T is. Let's just solve for U capital T in terms of X capital T, and then later on figure out what X capital T should be. So if you write out the only term that depends on U capital T, that last one, and you write it in terms of UT and XT, where XT is this really, really complicated function, and UT is an optimization variable, because their cost is quadratic, this is what that term looks like. It's some constant plus this quadratic function. And I'm going to call this Q of XTUT. It's a very loaded letter to use. It actually does mean Q function, and you'll see why in a second. But for now, this is just some function of UT. It's a quadratic function. So if I want to figure out the value of UT that minimizes this in terms of XT, how can I do that? How can I find the UT that minimizes this quantity? Yes? Right, so we can take the gradient and set it to 0. Conveniently enough, quadratic functions are convex. So optimizing quadratic functions is actually quite easy. It corresponds to solving a linear system of equations. So the notation here is going to get a little bit nasty. There's going to be a lot of linear algebra. But don't worry, it's just linear algebra. So if you see me write something like capital C with a subscript UTXT, that means that it's the portion of this matrix that's in this corner. If you see me write CXTXT, that means that it's like the top left piece of the matrix. And the same for the vector. If you see me write little c subscript xt, that's the top part of the vector. Little c subscript ut, that's the bottom part. So if I take the derivative of this with respect to U capital T, I've done the math for you here. This is the derivative, but it's very easy to calculate this derivative because all the terms here are either linear or quadratic in UT. So the linear terms just turn into whatever is multiplying UT. The quadratic terms turn into the UT times the thing that's multiplying it. So if you take the derivative of this, and you can check this at home, you get c UTXT. That's the off-diagonal portion of this matrix times xt. You get c UT. That's the lower right portion of this matrix times ut, plus the vector component c ut, this piece. Okay? So that's the derivative. You set that derivative to 0, and basically you have a bunch of terms that don't depend on ut, so the first one and the last one, and you have this middle term that does depend on ut. So what you do is you subtract both of the constants, put them on the right-hand side, and then do c ut inverse to both sides. So when you do this, you get this answer, right? So I've taken these two terms, I've put them on the right side, and there's a negative in front, and then I get this matrix times ut, so I invert that, I'm left with just ut, and then the inverse over here. And that makes a lot of sense. The way that you find the optimum of a quadratic function is you solve a system of linear equations. So a lot of symbols, a lot of linear algebra, but in the end, a very simple equation for the best ut. And for simplicity, to declutter our notation, we'll write U capital T like this. We'll write it as some matrix kt times xt plus some vector little kt, where big kt is this thing and little kt is this thing. So all I've done is I've just renamed the symbols in this equation. So now we expressed the best last action as a linear function of the last state. So that's the base case. And now we'll proceed backwards in time recursively. So this is what we know so far. This is the thing that we minimized. And since U capital T is fully determined by X capital T, you can now eliminate it by substitution. So everywhere where you had U capital T, substitute in the right-hand side of this equation, which doesn't have a UT anymore, it only has an XT. So now you basically remove one of your optimization variables. And that's great, because once we remove all of the optimization variables, we'll have a solution. All right, so now that I've substituted in my equation for UT, I have another expression that is only a function of x capital T. And I'm going to call that v. So q is a function of xt ut, v is a function of only xt. So this is what it's equal to. It's terrifying, but it's just this thing expanded out. It's terrifying, but it only has two types of terms. It has linear terms and quadratic terms. It also has constant terms, and the constant terms you can disregard. So that means that instead of writing it in this terrifying way, I can write it in a much simpler way as just a matrix component, vt, and a vector component, little vt. Now, the vt and the little vt are given by these scary equations, but you just kind of sweep that under the rug and stick with a nice simple form. All right. So now what we're going to do is we're going to go backwards one step. We'll solve for the second to last action in terms of the second to last state. But here we have to keep in mind that now ut minus 1 is not just going to affect the cost at time step t minus 1, it will also affect the cost at the last time step because it affects xt. How does it affect xt? Well, it affects it through the linear dynamics. So this is where the linear dynamics are going to come in. We know that x capital T is a linear function of xt minus 1 and ut minus 1. So we'll do the same substitution that we did before. Before we substituted in our equation for ut, now we'll substitute in this equation for xt. So we'll eliminate xt as well and replace it with the right-hand side of this equation, which is now expressed entirely in terms of xt minus 1 and ut minus 1. And once we've done that, we've essentially shortened our sum by one term. We'll completely remove that last term, and then we'll be back to the base case. So here is the expression for the cost of the second to last step. It's quadratic in ct minus 1 and linear in little ct minus 1, and then it has this other term which basically describes how it affects the last state. Now this v, we had that v before. The v is just this thing here, right? So v is a function of x capital T, and all we're going to do is we're going to plug in our f in there, right? So this is our v. And we'll just replace x capital T in this equation with the right-hand side for our dynamics. So when we plug that in, here I've just written out this, the right-hand side of vxt, but I replaced xt with the right-hand side of this equation. So everywhere I had xt before, now I have ft minus 1 times xt minus 1 ut minus 1 plus little ft minus 1. And again, it results in an alphabet soup, kind of a really messy equation with lots of algebra in it, but just like before, it has only two types of terms, linear terms and quadratic terms. So I can collect all my linear terms, collect all my quadratic terms, and simply add the quadratic portion to the quadratic portion here, add the linear portion to the linear portion here, and end up with some other quadratic equation. So instead of having capital CT minus 1, I have capital QT minus 1, where capital QT minus 1 is CT minus 1 plus this quadratic portion, and little qt minus 1 is CT minus 1 here plus the linear portions. So you just collect the terms, and you get something that is, again, has a quadratic portion and a linear portion. And now we're back to a form that basically matches what we had in the base case. It's just the c's became q's, but it's still quadratic. So that means that we can solve for the optimal ut minus 1 in exactly the same way as we did before. So in case you want to know what qt minus 1 and little qt minus 1 are equal to, here I've just filled it in for you. Just like before, you calculate the derivative, set the derivative to 0, put all the constants on the right-hand side, multiply by the inverse of the matrix, and you get ut minus 1 is, again, some matrix times xt minus 1 plus some vector. And if you want to know what the matrix and vector are equal to, here they are. They actually look pretty much exactly the same like they did before, only all the c's have been replaced by q's. Okay, so now we've got ut minus 1. Just like before, we're going to express xt minus 1 as a function of ut minus 1, eliminate ut minus 1, and repeat. So then we'll eliminate these variables one by one, starting from the end of the trajectory, going all the way to the beginning. So this results in a backward recursion method, where for every time step from capital T all the way backwards to 1, you first calculate your q and little q matrices. That allows you to express your q function as a quadratic function of xt and ut. Then you calculate the ut that minimizes that, which is a linear function in xt. That allows you to eliminate ut. So here's the big K and here's the little k. Then you express your value function v entirely in terms of xt with ut eliminated. So that gives you the v. And then you can recurse back to the previous time step and plug this v into the q in the time step before. And then you repeat this. So you can think of this visually, that there's an axis for time and an axis for state. You first calculate your best action at the end. Let's say this trajectory is of like 100. You calculate big K 100, little k 100, big K 99, little k 99, and so on, all the way back until you figure out u1 as a function of x1.
You still need to know
x1 is. So now we're ready to actually finish that.
So you still need to know all like the actual reward function.
The dynamics, right? It's not just the reward function. True.
Yeah, you need. Yeah, that's right. You need to know the full dynamics.
Yeah.
Yeah.
Which is why you can only use linear dynamics.
Yeah, but that's still.
That's important. Yeah.
Yeah.
That's important.
But how would
No,
that?
I
How
know,
does
but
that
how
make
would
it
you
better?
know?
You'd still be totally guessing
If you
if
have like
you.
a robot, you know the dynamics and how it moves.
Oh, so you mean there are specific use cases that make it a lot easier
Yeah.
to find linear dynamics
Yeah.
for this sort of thing? Ah.
Yeah, but the cost function is. How do you get that?
They make that.
You make
'Cause like
you
I-
make it up.
Make it up.
Okay.
Like you limit the speed that it moves up and how much it moves up.
So you just say like. Okay, so that's hand
Yeah.
coded
Mm.
basically. Yeah, so I understand the dynamics because that's basically using physics.
Yeah.
So I do get that, but okay. So the reward is just
Hmm.
That's
handcrafted.
probably the main problem to design rewards such that it would solve your optimization problem, but to design it in a way that it fits on the requirement of being quadratic term, for example.
Yeah.
And then you go with constraints and stuff, but that's even worse.
Flashback.
Your stuff, right?
Yeah, kind of.
Can you accommodate LCARs or any optimal control algorithms yourself?
Basics.
I'm
You
trying to.
just use solvents, right?
Oh,
MPC. Well,
MPC.
but you've got it up yourself. Oh no.
Yeah.
Really?
Yeah.
So when you were to use it, or if you were to use this
Yeah.
for a robot model, I'm trying to visualize sort of a case where you'd have this. You'd have like, I don't know, 100 steps, and what would that be like? You'd have your robot arm try to put a cup full of peas
Yeah.
into another cup, that sort of thing, and you would basically look at that state, and then you would think of it like backwards from having poured them all in, and then what was the last thing you had to do that?
Yeah. So
And rewind.
like for doing something like so abstract, like
Yeah.
like that's why like making these cost functions is so hard, because how do you like define what you want to do in
Yeah.
terms of that? If,
Mhm,
like
mhm.
you can do it in sort of simple cases, like say you want a car to drive around the track or something.
Yeah.
Like you measure the distance between the lanes, and then
Mm.
like you give it positive and negative cost for like moving forward.
Yeah.
So you can sort of like make those very brittle versions of the cost function.
Yeah.
But like once you try to do something more complicated that you can't really describe, like you know, pick up something or put something in,
Yeah.
like it kind of just falls apart.
Yeah.
Okay.
So this is really for things that you kind of can locally decide whether it's doing a good job or not.
Yeah.
Yeah.
So like the way you do it practically is you like split the problem up into like the smallest components. You just have one little thing that you know exactly what it wants to do.
Yeah.
Right. Yeah. So it's
Single
nothing for
action.
sparse rewards. You
So
wouldn't get very far.
You can like
Yeah.
just run,
Yeah.
then you end up with like a big.
Yeah, and what was confusing
Yeah.
for the, when I looked at it for the first time, that you actually, unlike in RL, you go through the whole algorithm every single time when you go into a new state. So at each time step, you solve the whole thing with a backward and forward pass,
Yeah.
and then you pick the best sequence of action, and then you apply just only one action out of it, the first one. And then when you occur in the next state, you do it again, every single time.
Why would you do it again? Because you end up.
Because new state, new stuff, you need to do the same thing again.
But you end up in the state that the dynamics has already told you where you would end up.
If you're in the real world, that's not always a good assumption.
Yeah,
Like if you think you're going to move a certain amount forward, but the friction's slightly different, you end up slightly differently.
Right.
And you do it over heaps
So-
of time steps.
So
you
it's
end up
like
in a really,
yeah,
really
closed
good place.
open loop
Yeah.
thing,
Right.
and it's just boom.
You also need to know where you want to end up.
Yeah.
So it gets cheaper the closer you get
Yes.
to the exit.
So the way I
Yeah.
did it with MPC is like you just have a really short time horizon. So you plan out 5 or 10 time steps, but you just do it constantly.
Right.
So you know 100 time steps, like that would take forever to solve.
Yeah.
But if you're just doing like 10 time steps and you're just constantly updating your plan, like then it's
So would that be like sort of an episodic task that has like a, say in this case, a 100-step window? Is that how you would look at it, or would you say you chop up your entire trajectory that is limited as a little like episodic task, and then you would say, okay, I've got let's say 10 steps, and then you get to state 9, and then you have to calculate through 9 steps back, and then you get to 8, and then you have to calculate through 8 steps back. Would you unspool it that way?
Sorry.
But you ship the window.
Yeah, that was my question. Whether you would use a window and then you would have like continuous movement that
it's
way,
moving window.
or whether you would only use it.
So
So
you
you
almost
don't
like
have to use it for episodic tasks alone. It doesn't have to be.
No, so you can just look
Yeah,
like
yeah.
10 time steps ahead.
Right,
How you
yeah,
find time
yeah,
steps.
yeah.
But yeah, as you look further and further, like it takes longer and longer to compute. Which is why the dynamics need to be linear.
And it's not parallel, and you cannot parallelize all that stuff because it's
It's sequential.
Yeah.
Yeah.
backup,
And then
development stuff,
it's just
and
like
all that.
yuck.
Yeah, because like how in your case, like how big was your x vector, for instance?
Like the last one I did was literally just like position x, y, and then velocities like v, and y, and then
Oh, that's not too bad then.
Yeah.
But then the actions, is that the...
So the actions are acceleration, and steering angle.
An angle is discretized to it.
So but then the dimensionality is pretty small, right?
Pretty small.
So what's so heavy about it?
It has to be real time. So if you're trying to actually do something, you have to solve like where you're going to be, take into account physics.
The fact that you're actually
and do
already
it,
moving.
Yeah, and do it like constantly, like, you know, kind of, put the train tracks as you're going.
Yeah.
Like,
Yeah.
So that's, well, this is for like a real system, but that's more often the constraint, that it has to actually happen in.
You have to compute it faster than it's
Yeah.
happening.
Yes, it's just like there is no inference. It's always
Yeah.
like training happening
Mhm.
all the time. Even when you want to apply the system in just some production level,
Yeah.
you still solve the problem every single time. You just
Yeah.
new in a state.
Which, you might control it by, slowing down how your process goes so you can do something a bit more complicated.
Yeah.
Real world's annoying.
But to invert the matrix, that's like, what is it, like maybe...
It's expensive. It's expensive.
Expensive.
I'm sorry.
Yeah.
Actually, you said learning. This is a backward recursion because you've got your window of so and so, but I don't really understand where the learning happens per se.
There
Because
is no learning.
Yeah, from one step to the
Essentially,
next, you don't have.
You just calculate the solution and that's it.
But if the
you apply it and you forget.
Yeah.
So if the bottleneck is inverting a matrix, let me see if I can get this. So if it's like a small enough matrix, you have a closed form expression to do that, right? Can't you just actually like write down this is the inverse of that? Or it's still a bunch of operations, but
I mean, you just run the huge Gauss-Jordan elimination.
Okay.
How many times? Yeah, but essentially, yeah. But it's not small. I mean,
It's not small.
it's just an example when you have just position of just one joint or whatever it is, or a car. But if you go even like for pendulum, for example, it's fine. You just get one joint and you apply force, torque force. It's just super simple. But then you go to a 2-joint, for example, pendulum. Ooh,
It's impossible.
nice.
Yeah,
Yeah,
one
one
it's literally like you can't solve. Probably someone can, but like it's just orders of magnitude harder.
Yeah.
Even though
Just
it's
couple
seems
more
simple.
dimensions and it doesn't work.
okay.
As well as RL in general. So
Wow.
And that's so. What are the actions if you have 2 joints? It's just 2 actions, 2 torques.
yeah, but how do you set up the cost?
Oh, yeah. That's a double pendulum. Okay.
Yeah, calculation
Okay, fair
and
enough.
designing the cost.
Yeah. I
It's
see.
crazy.
Yeah. No, okay. I'm well aware of how hard that is. Okay.
Which is what's so like attractive about RL is that like if you can sort of set up the reward function correctly, you have a big enough simulator, enough GPUs, like you can do things that kind of impossible.
Yeah.
I think I just saw a video tomorrow, like OpenAI had solving like a Rubik's Cube with their little hand.
Yeah, but they had just like how much the whole factory of those hands just.
I don't want to see how like the sausage is made. It's just difficult.
So this is basic, like regular control theory.
Yeah.
Like I was confused. Like I know none of these notations, so I was a bit lost during this video.
Yeah, it's a lot of data in
No,
here.
today.
Very ugly.
Yeah.
You did.
Oh, there's no RL in this.
Yeah.
I mean optimal.
Yeah. I have no idea what that field even does, but
Here there's no reinforcement and no learning. So
no, yeah.
Yeah.
So they say like, oh, we know what it needs to do, and we calculate back from that how to do it. Okay.
Yeah, but like Patrick just said, the thing is that in order to do this in the real world, you have to do this every time you take a step.
Yeah. Okay.
So yeah, there's no. I guess could you? Is there a way that you could? No, not in real time. Anyway, you could probably collect some observations as you go through, and then try to make your F and C better or something, but not in real time.
Yeah, but the difference here that this guy, this algorithm, gives you 100% accurate solution, whereas when you try to learn something, there is no guarantee just for high performance, excellent performance.
Yeah, but that's
this is a big advantage of these methods.
Yeah.
They just provide you just closed, optimal
Yeah.
solution.
And if you have to like rely on something to work,
Like a car.
or just any kind of like machinery,
Yeah.
like you almost want it to be more reliable than actually like better. Like you want to be able to depend on what it's going to do exactly, even if like the actual dynamics are simplified, rather than trying to sort of get the most optimal thing.
Yeah. So is this the sort of thing that you would think might be driving those mining trucks? Because the routes are fairly simple, fairly straightforward, as far as I understand. In those mines, the routes that the trucks are taking are fixed. They're not necessarily flexible. They don't have to take detours and react spontaneously. So that would be that sort of thing where they have to be able to calculate the times that it takes at that weight and so on to get here and there for fuel costs.
It might
and
even
stuff.
be something sort of like if they're just doing the same mine, they can sort of pre-program a set of waypoints and then have a simpler controller just to say, stay on these waypoints.
Yeah.
And then they can limit the speed or something.
Yeah. So I would imagine like this could be the way that they could do this for like various weights. Like not every single load would be exactly the same weight, so it might not. A simple programming.
Yeah. So that would change your dynamics. But you can see like where this just like immediately falls apart if like anything about your dynamics changes. Like because
Whole
you have to solve
But still, this is what people use in robotics, as far as I'm aware. Not RL. Like Boston Dynamics and stuff, they sold out this stuff.
Yeah. So they.
But way more complicated, of course.
Yeah.
Still.
I have to go. So could we maybe like just either watch this at home or watch this next time?
Could be a good warm-up to watch the last 10 minutes next time, because this seems that if I understand correctly, he's going to.
We know x1, which means that we can now perform a forward recursion and actually fill in numerical values for all the u's back to the front. So you kind of unzip this thing, unzip it back up, and then you get an answer. So now you have a forward recursion from the first time to the last,
10 minutes.
where you calculate your action as big K xt plus little k. You just use the k's that you've already got, and then figure out the next state by applying the known dynamics.
So how about we grab those 10 minutes next time to get back into it, and then we'll start from here, 1 hour 10, and remind ourselves of how the linear case worked, and then he's going to the nonlinear case from this, and then we can get into the policy gradient.
Okay. And then we write one of the exercises. Is that the idea?
Yeah, I'll put the links to everything on the on Slack, so that we can see everything, and that way we should be able to. I was just gonna use PyCharm and just use DimDLab or something.
Yeah.
Just make a notebook or
The
a
only
Python
thing
file.
is, some of them rely on Mijoku, so
Yeah.
you just need the I use the RoboSchool,
Mhm.
which is a
Okay.
nice free version. So
Yeah, alright.
just to-
I'll try.
But it uses the same kind of
Yeah.
same
environment.
kind of.
By the way, RoboSchool and Mujuka won't run on your Windows laptop. Congrats. Most likely. Or
Yeah.
it's whole pain in the ass. One is
No, I'll bring my own laptop anyway.
There was I think I remember seeing there were instructions on OpenAI how to deal with each case and to make sure that they work.
Yeah, but the problem that
But even
they
Atari
do not
doesn't work
support
on it.
Windows platforms in
No.
general. So it's got to be Unix system.
Yeah.
Which is.
Yeah, it's the same with Atari. It doesn't work with Windows. We're still on public. We're still. There's still a camera running, so. I'll be saying yes.
Well, consider that it's 6. I'm happy to switch the camera. So thank you, Internet, as usual. I hope next time we'll have more viewers than today because we had none. So, either that or pure packed YouTube, and we don't know that yet. So yeah, till next time.